All right, so section 5.4, Calc 30 here. This is the second derivative test. So this is in our curve sketching chapter. And we talked about, what significance the first derivative has in noticing where the function is increasing, decreasing. Therefore, we can determine where local maximums or local minimums are. We also did talk about the second derivative yesterday, in that the second derivative tells us where the concavity is, right? Or where the points of, where the intervals of concavity are and where the points of inflection are. So the second derivative tells us about concavity. And the second derivative test is actually a way, it's a bit of a shortcut. It's a way of determining maximum and minimum, so local max and minimums, without doing sign analysis, okay? Now, you won't opt for this every time because probably finding the second derivative can be pretty tricky. And it might be a lot less work to do sign analysis on their first derivative than it would be to find the second derivative in some cases. But the fact remains that you can use the second derivative to determine where you have a local max or min. So let me just zoom in here a little bit and show you my clever drawings here. Now, this is just some random sign analysis that I've done with like fake factors over here. And for whatever reason, these are yielding a negative for a first derivative. So this is first derivative. I've got negatives here. I've got a 0 at this critical number. I've got a positive, then I've got another 0, and then a negative and 0 and a positive. So this is just a random sign analysis. And what we've done before is we've determined from using just this picture right here, we've been able to determine that we have, at this critical value right here, we have a local minimum because the tangents are negative, then the tangent is 0, then the tangents are positive. And so if it goes negative, 0, positive, that's a local minimum. We also look at this and we do the same thing for the other ones. So we have positive, 0, negative, that's a local maximum at C2 here. And then down over here again, another C3 is local minimum. All right? So that's what we've done before. Now, if we were to graph this, let's say the graph looks something like this in red, where we have a local minimum right here, a local maximum right here, and then another local minimum over here. Well, what we notice, and we kind of touched on this a little bit yesterday, is that in the interval containing the local minimum, this graph must be concave up in this immediate area. So let me say that again. In order for this to be a minimum here at this red dot, the graph needs to be curving up like this, right? Because it's got to have a concave up on this side, and then there's a concave up on this side, and then there's your local minimum. For a local maximum point, the concavity immediately surrounding this local maximum right here, the concavity has to be concave down. All right? Now this, again, one more time, so this is a local minimum, and the concavity, if you take a little snapshot here, the graph itself has to be concave up in this little area. So what does that mean? Well, that means that if we have critical numbers and we're trying to determine if these are local mins or maxes, and if it's easy for us to take the second derivative, we take the second derivative and we plug the critical numbers in to determine what the concavity is at that point. So again, this is a way to bypass sign analysis, which at times, this may be a lot easier to do the second derivative test. And you'll be asked to do the second derivative test as well to prove local max or min, or to identify extrema. So here's the little note that goes along with these little drawings. The note is this: at every local minimum, the concavity is positive. And that is, this is very important right over here, that the second derivative has to be greater than 0 or positive. At every local min. Anything you can draw The concavity has to be. Now this is also, and I will talk about this a little bit later. But if you ask about cusps or corners, this does apply when the function is differentiable at the point, and I'll talk a little bit more about that as we go through. But for polynomials and where we don't have cusps or corners or something strange like that, then it's always positive, which will be 99% of the time probably for you. And conversely, at every local maximum, like I drew over here, then the concavity is negative. So it opens down, and just in that region. So therefore, the second derivative must be negative. All right, any questions so far? Are you with me so far? Pretty straightforward? Okay. So what is the actual second derivative test here? Let's kind of formalize this a little bit. So for every critical number, so you're going to focus on your critical numbers, which again are the x values that cause the first derivative to be 0. For every critical number, we can determine whether it's a local max or min by evaluating the second derivative at each critical number. So here it is, evaluating the second derivative at each critical number. And in concert with the notes that we just took, here's another little summary. So if f double prime of critical number 1 that we test, if that's positive, then you know we have a concave up section. That would be a local minimum. And if the second derivative evaluated at C2, let's say another critical number, if that ends up to be negative, then we have a concave down section, which means that this graph, whatever it is, must be, oops, that's pretty bad. Concave down here, so this is the graph, so that must be a local maximum. All right, so, and in summary as well, you don't have to do sign analysis this way. So are you ready for an example? All right. I'll take your enthusiastic silence as a go-ahead for me to go. All right, let me just erase this because I did this before. Okay, so I do have some steps on the side. If you want to write these down, you can. These will be on the instructional video if you want to just watch back. But a lot of this is intuitive, but you can write this down if you're a step-taking person. So find the local max and min using second derivative test. That would be a typical type question you would get for this polynomial. Maybe I'll zoom in just if I can without destroying the view here. All right. Okay, so step 1, find first derivative. Yes, you need to find first derivative before you find second derivative, obviously. But the other thing is we need to identify critical numbers. So we do need the first derivative is very important in this process. In the second derivative test, the first derivative is super important. So what's that going to be? 4x cubed minus 24x squared. Okay. And can we find critical numbers? Yeah, let's let this equal 0. And I'll factor here if I can. So I'm going to take a 4x squared out. I'm with x minus 6, I guess. Okay. Now, the critical numbers will be x equals what? 6 and 0. Right. So those are my two critical numbers that it appears that I have. So I would like to know if this represents a local max or min. Now, if it's neither, okay, if it's neither, then it's probably going to be, as you see down here, a 0. Okay, the second derivative will yield you a 0, or it could be undefined. So what we're looking for is the evaluation of the second derivative at each of these points, and we're determining if they're positive or negative. That will tell us if we have a local max or min. So second derivative, first things first, is going to be 12x squared minus 48x. All right. So let's put 6 in here first. So when you evaluate that, the second derivative evaluated at the critical number x equals 6 is positive 144. Positive. So that rate of change of the rate of change is positive. This is acceleration. This is concave up in the graph. It's a concave up section. So what's that going to be? It's concave up. So it's a local what? Min. Yeah, it's a local minimum. So and you would probably list that point, put your 6 into the original at 6 comma, whatever. Okay? So it's concave up, local minimum at. We'll worry about that later. So we'll do another evaluation here at 0, which is, well, what's that? 0. Okay. So what happens at 0? Looks like there's neither a maximum or minimum. Plug critical numbers into, 0. Yeah, I think that should be no inflection point at this x value. Or it's not defined, whatever. So yeah, so here we go. X equals 0 has no max or min there. So we don't really know too much about the graph at this point at x equals 0, whether it's defined or not, but we know it's not a local max or min. Okay? So negative 432 is this value here, I see. So that's your local minimum. Okay? And I think what we should do is let's maybe graph this. Let's graph this and just check that out. So x to the 4th. Actually, I'll get you guys some graphing calculators, and I'll do this on Desmos as well. All right, so here's the graph, and notice that we do have a local minimum down here, 6, negative 432. Awesome. And in this area here, it's not concave up or down at this point. So if we chose a point over here, then that would be concave up, or a point over here, that would be concave down. But because this is the point of inflection, right, there's no concavity there, so it is a point of inflection, not a local max or min. So, okay, yeah, no, I shouldn't have changed that then, sorry. I changed this, I shouldn't have changed this. So when we have a 0, yeah, for the second derivative, this is where the inflection point is at this value. Yeah. There's no local max or min, but that would be an inflection point there.
Is it more than one concavity? Like, is there multiple ups and downs?
Well, there could be, yeah. In this one, it just looks just like this, and then that goes up forever and up forever. We're done there. So this is so you have concave up here, then you have concave down to about here. There would be another point of inflection. We didn't find the points of inflection here. We're just testing the critical numbers to see if they're local max or mins. So there might be other points of inflection for sure. We haven't gone there quite yet. But it just so happened that one of the critical numbers where the derivative is 0, right? It's the derivative of 0. That's also a point of inflection. All right. Okay. Here's another one. I won't get you to do this one. Let's just walk through it. So again, the same thing. We find the first derivative. We factor to find critical numbers. Here they are. I then find the second derivative, and over here, and then I plug each critical number in to find out what sort of value the second derivative has there. So at 3/4, in this case, we have a positive value, so that's a concave up. That'd be a local minimum here. And at 0, I guess 0 is just 0 as well, so there's nothing there. And here's the graph. So very similar to the one we just did. Local min over here, and no local min over here. Okay. All right. I'll give you your assignment to work on here. I have done some of these questions here, so if you have trouble, let me know. But you can start by doing 1AC, 2C, and 3AD.